Okay, hello YouTube. Yep, just want to quickly wrap this up. So in the last video, we are talking about this z function, and we see that z in the boundary layer is several orders of magnitude bigger than this CMU and this the square root term. So if you take a look at the max function, it is this yellow curve, okay, this maximum function, and you want to take, okay, this is the maximum function of these two numbers, and of course we see that these z values, as y plus increases, it will get smaller and smaller. Not only that, in actual fact, this term actually gets increasingly large as we go towards the turbulent bulk layer. In the boundary layer, this term is almost negligible, but as you increase your y plus to the point where you reach the turbulent turbulent layer, and this thing kind of increases dramatically. Okay, so what you might have, okay, it's you might have this term. Okay, I'm now finally going to start talking about this argument term. I can't plot out exactly what the graph will look like for the whole thing, but at least in the boundary layer, it will look like this. Okay, yeah, you're looking at the term that's about to be, you know, raised to the fourth power in here. It is this term inside here. Yeah, in the boundary layer, this thing is humongous. So normally we will not be using this term in the boundary layer. We'll use either of these two terms. And if we take a look at this, it's like going at some fixed value, and then suddenly it drops, and then it goes to another fixed value. Okay, so this is the function. All right, so it goes like that. So we just call this the argument inside, and then it goes down and goes like that until y plus equals to yeah, y plus can be 30, 300, I don't know, as long as it's a boundary layer, right? Y plus, and then there's the argument. So these are just example values. All right, these are just example values, and what happens is that you have this other humongous term that starts. So you have this humongous term, which is this z term. It starts out big in the turbulent, the viscous sublayer. Then it rapidly shrinks till it reaches the turbulent portion of this simulation. Of course, I don't have a way to just estimate this other than the use of raw functions, but you can see that this term actually is pretty small, or in fact zero, inside the viscous sublayer and the turbulent sublayer according to this model. After that, this term will start increasing, and then this term will the denominator will increase, and then the this whole term will start to decrease. So the pattern is you probably start out very big, and then you will go here. All right, so if you want to take the minimum of these functions, you probably take this, you take this, and then you take this. So whatever it is, assume it shows that the argument decreases with y plus, and that's the correct behavior. So if the argument decreases with y plus, I mean, okay, if the argument decreases with y plus, then okay, I'll have the argument equals the minimum of this and this. Let's say this is the 6.25, and then it just jumps down very quickly. All right, and then we try and have a tangent argument to the fourth. Okay, so this I'm just taking zeta goes 100. Okay, of course you increase your zeta, you increase this numerator value, of course it will change the results a little bit. That means if you increase this, the term, this whole z term gets smaller in general. Okay, so hyperbolic tangent of this argument to the fourth power. Okay, so it is 1 near the walls. You can see this 1 near the walls, and then okay. Alright, so hyperbolic tangent of argument to the fourth power. Alright. So we have this thing. Yeah, it's just 1 at the walls. There's really no argument to say, or no argument to say. So okay, we show that for this typical z values with zeta equals to 0.01, 1, and 100, f1 equals to 1 in the boundary layer, which is what we want. F1 equals 1, that means the K omega model. Okay, if F1 equals to 1 in the boundary layer, F1 equals to 1 in the boundary layer, this term disappears. That means we are using the traditional K omega model. F1 equals 1 in the boundary layer, meaning to say that the phi, if you take a look at this, we will only use phi 1 because 1 minus F1 is 0. So that means phi 2 is not used. These are the, phi 2 is the constant used for the K epsilon model. Phi 1 is the constant used for the K omega model. So we see how this blending function works. So this turns on K omega in boundary layer always. Alright. And so the only time that this doesn't really apply is that if this term increases, okay, so I would say this, but as this term increases, then F1 decreases. So this thing will increase in the turbulent region. F1 decreases to give to reach 0, and thus turn on the K epsilon model. Okay, so this is how the K omega SST blending function works. So of course the hyperbolic tangent inside this boundary layer is just 1. There's nothing exciting there, so to speak, regardless of the value of zeta. And how do we know the values of zeta are pretty typical or in the right range, or at least in the the answers of zeta don't change, you know, this analysis. We can look at typical zeta value. Okay, so we go to like a typical friction velocity over here in this IChemE. This is from a chemical, I think, chemical process safety website. Okay, so U star, this is the friction velocity, has a typical value ranging from 0.05 meters per second in light wind to about 1 meter per second in strong wind. So if we were to use the example of air, U star equals about 1 meters per second, sure, and U star equals 1 meters per second. So this is what I have here: light wind and strong wind, typical values of U star. Rho is about 1 kg per meter cube. That's a given. And then the kinematic viscosity of air, I got it from this Engineer's Edge website, which is over here. Alright, the kinematic viscosity of air is about 1.48 times 10 to the minus 5 meters square per second. So this is the kinematic viscosity of air. I get this zeta value to be about 2.19 times 10 to the minus 10. And this is very small, and you will make your z value very, very big inside the boundary layer. So if the z value is very, very big in the boundary layer, for sure we will be using these two terms over here, and your hyperbolic tangent argument will be equals 1. That means your f1 will be equals to 1, which means that your k omega model will activate them. Okay, only when this thing kind of increases a lot inside the or rather this whole term increases, or this whole term increases inside the turbulent the bulk fluid region, then you'll start to see this term decrease such that it is below this curve here. Then you will start to have different effects coming on, and you have the k epsilon. All right, and then in the boundary layer, so you have a k omega. Of course, why you have a hyperbolic tangent function? It is because, okay, what's this? Okay. Anyway, yeah. Why do we have a hyperbolic tangent? It's because you see that this argument inside, it's a very you have pretty much abrupt changes here. So to have a smooth transition, you use this hyperbolic tangent function to make this thing actually smoother. So that means you have f1 and you have a y plus here. So you'll have this sort of transition. Okay, so that's roughly the shape of f1, roughly f1 shape with respect to y plus. So that should be expected. Okay, so that is it for our estimation of f1. Okay, so hopefully that gives you some in-depth understanding into the blending function and how it works. But yeah, I think yeah, that's it for now. It's a pretty heavy last few videos where we try to get wall functions for all of these values. However, that kind of helps to solve some of the functions as well. Let's say for f2 here, it's pretty much the same form as here, so the work's already been done. And then I can go through all the other terms qualitatively. But for now, I want to stop this video, kind of get a break. It's been a lot of explaining to do. Okay, so thanks for watching. See you guys again. Continue with the qualitative discussion of the K Omega SST. I mean the other terms in it, not just the blending function. And this blending function is probably the most critical thing there. Yeah. So thanks for watching. See you guys next time. Bye bye.